The last failure of the octet rule is valency expansion. So if you have heavier elements in the third row and below on the periodic table, they can often expand their octets. So they can take dectets and have 10 valence electrons or even dodectets. Let me give you a couple of examples. Let's say you're trying to draw a Lewis structure for the PCl5 molecule. You might start with the handy hints, and the handy hints will tell you that you have 48 electrons required and 40 electrons available. And when you subtract one from the other, you get 8 electrons that should be shared, and that makes 4 bonds. But how can you possibly draw this molecule with 4 bonds? You can't. P is the central atom because it's the unique element and the most electropositive element in this case. And if I want to draw 5 chlorines around it, I'm going to need 5 bonds. So right away, I need to throw the handy hints out the window for this molecule because the octet rule is being disobeyed. Remember, the handy hints are fully based in the octet rule. So here, I have a situation where I need to look at those 40 available electrons and kind of spend them by building the molecule in an ad hoc way. So I just spent 2, 4, 6, 8, 10 electrons. I have 30 left to spend. So I'm gonna start by filling up the octets of the chlorines and see if I can spend those 30 electrons that way. And it turns out that I can. So there are the extra 30 electrons. So if I go through and actually just look at the final molecule and count up all of the electrons in it, it should add up to 40. Oops, I erased one of the bonds by accident. I was trying to erase these highlighted areas. I want to clean up my molecule a little bit so you can look at it. All right, here we go. Boom, boom, boom. So if I count up all of the electrons, the 5 bonds makes 10 electrons plus the 30 lone pair electrons around all the chlorines. That makes sense. So this is a stable molecule. Phosphorus is just fine taking a dectet like this. And it is very happy to form a compound this way. It's only going to be the central atom that expands its octet for reasons that we'll discuss next semester. So it's never the terminal atoms. It's only the central atom that gets to expand its octet in this way. Let's do another example of a valency expansion case. I would like to draw a Lewis dot structure for the compound SO3 that results in a formal charge of 0 on sulfur. Now, you should recall that in a previous lecture, we drew a Lewis dot structure for sulfur trioxide, and we actually drew 3 resonance structures for it, and they look like this. Okay, so there was this resonance structure, and there were also 2 other resonance structures that were equivalent, just rotated 120 degrees. So we had built this resonance structure previously in a previous lecture. Now I want to see if I can draw a different structure with a formal charge of 0 on sulfur. Now, if I find sulfur in the periodic table, it's a 3rd row element. So sulfur is perfectly capable of expanding it beyond the octet. So I'm going to try to play with the molecule. I can't use the handy hints here because I'm going to be going beyond the octet for sulfur. So I want to try to build the molecule in a way that reduces the formal charge to 0. So first, I'm going to take one of the lone pairs here and move it over to become a double bond. So basically, I'm just taking those 2 electrons and distributing them a little bit differently. And the reason I decided to do that is because I want to reduce the formal charge on sulfur. So I want to have a situation where I have 6 minus 6 giving me a charge of 0, right? So I'm going to need to have half of the bonds, basically. So I should have 12 electrons around sulfur. So then when I count up half of the bonds, I get a 6 to subtract from the 6 electrons that the free sulfur atom possesses. Okay, and I know that's a little bit complicated, but I'm drawing this structure because now, again, I'm counting up half the bonds, right? 1, 2, 3, 4, 5, 6. That's where I get this 6 to subtract from the 6 electrons that free sulfur would have. So now I have drawn a resonance structure where sulfur has a formal charge of 0. What's more, each of the oxygens has a formal charge of 0 because it's 6 minus 1, 2, 3, 4, and then half the bond, 5, 6. That's going to be the case for all 3 of these oxygens. So I have, in this sense, drawn a resonance structure that is now non-equivalent. So these are non-equivalent resonance structures. The question is, which one is better? Non-equivalent resonance forms, I'm going to call them. Which is better? That's a great question. How do we determine which is better? Now, we have to give sulfur, we have to adhere to the idea that sulfur is perfectly fine having, in this case, a dodectet. Okay, sulfur can easily accommodate a dodectet. Dodectet means that it can have 12 electrons around it. So this is a very stable arrangement for sulfur. It's just fine expanding its octet this way. So this resonance structure is actually going to be preferred because the octet rule doesn't matter in this case. And this is the one that really minimizes formal charges. So the truth of the molecule is actually closest to this structure, which has the formal charge of 0 in sulfur and the dodectet.